Welcome to our exploration of the mechanical properties of fluids. In this chapter, we'll dive into the fascinating world of fluids, liquids, and gases, and uncover how they behave under various forces. From understanding basic concepts like pressure to exploring advanced principles such as Bernoulli's theorem, this journey will help you see fluids in a whole new light. Whether it's the water flowing from your tap or the air moving around you, the principles we discuss are at play everywhere. Let's begin by laying the foundation with the concept of pressure in fluids. Pressure in fluids is a fundamental concept that describes how force is distributed over an area within a liquid or gas. Imagine pressing your hand against water. The force you apply is spread out across your palm. In fluids, pressure acts equally in all directions at a given depth. This property is why submarines and deep-sea divers experience greater pressure as they go deeper underwater. Understanding pressure helps us explain many phenomena, from the way water rises in a straw to how weather systems develop. Next, let's see how pressure leads us to Pascal's law. Pascal's law states that when pressure is applied to a confined fluid, the pressure change is transmitted equally in all directions throughout the fluid. This principle is the reason why squeezing a tube of toothpaste makes the paste come out evenly, no matter where you press. Pascal's law is crucial in understanding how hydraulic systems work, allowing small forces to be amplified and used to lift heavy objects. Let's see how this law is put into action with hydraulic lifts. Hydraulic lifts are practical applications of Pascal's law. In a hydraulic lift, a small force applied to a small piston creates pressure in a fluid, which is then transmitted to a larger piston. Because the pressure is the same, but the area is larger, the force is multiplied, allowing heavy vehicles or loads to be lifted with ease. This technology is widely used in car repair shops and construction equipment. The efficiency and power of hydraulic lifts showcase the real-world importance of understanding fluid pressure. Archimedes' principle is a cornerstone of fluid mechanics. It states that any object, wholly or partially submerged in a fluid, experiences an upward force equal to the weight of the fluid displaced by the object. This explains why objects seem lighter in water and why ships float. The upward force, known as buoyancy, is what keeps swimmers afloat and allows massive ships to sail. Understanding this principle helps us design everything from boats to submarines. Buoyancy is the upward force exerted by a fluid on an object placed in it. For example, when you drop a stone in water, it sinks because its weight is greater than the buoyant force. On the other hand, a wooden log floats because the buoyant force is greater than its weight. Buoyancy is essential in swimming, shipbuilding, and even in hot air balloons. It's all about the balance between the weight of the object and the fluid it displaces. Density is a measure of how much mass is packed into a given volume. For instance, a stone is denser than a piece of wood of the same size. Relative density compares the density of a substance to the density of water. These concepts help explain why some objects float while others sink. In daily life, density is important in cooking, construction, and even in understanding why oil floats on water. Equation of continuity is a principle that describes the conservation of mass in fluid flow. It states that the product of the cross-sectional area and the velocity of fluid remains constant along a streamline. This means that if a pipe narrows, the fluid must flow faster through the narrow section. This concept is vital in understanding how blood flows in our veins and how water moves through pipes. Bernoulli's theorem is a key concept in fluid dynamics. It states that in a steady, incompressible flow, the sum of pressure energy, kinetic energy, and potential energy per unit volume is constant. This principle explains why airplanes can fly and why a shower curtain gets pulled inward when the water is running. Bernoulli's theorem helps us understand the relationship between pressure and speed in moving fluids. Derive Bernoulli's equation, we consider a small volume of fluid moving through a pipe. By applying the work-energy principle and the conservation of energy, we see that the sum of pressure, kinetic, and potential energies remains constant along a streamline. This derivation is fundamental in fluid mechanics and forms the basis for many practical applications, from designing airplane wings to predicting weather patterns. Bernoulli's theorem has numerous real-world applications. It explains how airplanes generate lift, how carburetors and engines work, and why the speed of water increases when it flows through a narrow pipe. Even the curve of a soccer ball in the air can be explained by Bernoulli's principle. Understanding these applications helps engineers and scientists design better machines and solve everyday problems. Viscosity is a measure of a fluid's resistance to flow. Think of honey and water. Honey flows much more slowly because it has a higher viscosity. Viscosity is important in everything from lubricating engines to designing pipelines. It affects how easily fluids move and how much energy is needed to pump them. Understanding viscosity helps us choose the right fluids for different tasks. Coefficient of viscosity is a numerical value that quantifies a fluid's resistance to flow. It is determined by measuring the force required to move one layer of fluid in relation to another. This value is crucial in engineering and science, as it helps predict how fluids will behave under different conditions. For example, oil with a high coefficient of viscosity is used in car engines to reduce wear and tear. Stokes' law describes the force of viscosity on a small sphere moving through a fluid. It states that the viscous force is directly proportional to the radius of the sphere, the velocity, and the viscosity of the fluid. This law is used to calculate the terminal velocity of objects falling through fluids and is important in fields like meteorology and medicine. Terminal velocity is the constant speed that a falling object reaches when the force of gravity is balanced by the viscous drag of the fluid. For example, a raindrop falling through air eventually stops accelerating and falls at a steady speed. This concept is important in understanding how parachutes work and how sediment settles in water. Reynolds number is a dimensionless quantity that predicts whether fluid flow will be smooth, streamlined, or chaotic turbulent. It depends on factors like fluid speed, viscosity, and the size of the object moving through the fluid. Low Reynolds numbers indicate smooth flow, while high values signal turbulence. This concept is vital in designing pipelines, aircraft, and even in studying blood flow. Streamlined flow occurs when fluid moves in parallel layers with no disruption between them, like water flowing smoothly in a calm river. Turbulent flow, on the other hand, is chaotic and irregular, like rapids in a river. The transition between these two types of flow is determined by the Reynolds number. Understanding these flows helps engineers design efficient systems for water supply, air conditioning, and more. Surface tension is the property of a liquid surface that makes it behave like a stretched elastic sheet. It's why water droplets form beads and why small insects can walk on water. Surface tension is caused by the attraction between molecules at the surface of a liquid. This property is important in many natural and industrial processes, from forming bubbles to painting surfaces. Capillary rise is the phenomenon where liquid climbs up a narrow tube against gravity. This happens because of the combination of surface tension and adhesive forces between the liquid and the tube. Capillary action is essential in nature, helping water move up plant stems, and is also used in medical tests and ink pens. Angle of contact is the angle formed between the tangent to the liquid surface and the solid surface inside a container. This angle determines whether a liquid will wet the surface or form droplets. For example, water wets glass because it has a small angle of contact, while mercury forms beads due to a large angle. This concept is important in understanding how liquids interact with different materials. Mechanical properties of fluids are not just theoretical, they impact our daily lives in countless ways. From the way we drink through a straw to the design of cars and airplanes, understanding fluids helps us solve problems and innovate. Whether it's plumbing, weather forecasting, or even sports, fluid mechanics is at the heart of many modern technologies and conveniences. Atmospheric pressure is the pressure exerted by the weight of air above us. It decreases as we go higher in altitude, which is why mountaineers and pilots need to be aware of it. Changes in atmospheric pressure are also responsible for weather patterns and can affect our bodies, causing ears to pop during flights. Understanding atmospheric pressure is essential for meteorology and aviation. Hydraulic brakes in vehicles use the principles of fluid pressure and Pascal's law. When you press the brake pedal, pressure is transmitted through brake fluid to the brake pads, which then stop the wheels. This system allows for efficient and reliable braking with minimal effort. Hydraulic brakes are a perfect example of fluid mechanics making our lives safer. Why do some objects float while others sink? It all comes down to density and buoyancy. If an object's density is less than that of the fluid, it floats. If it's more, it sinks. This principle is used in designing ships, submarines, and even life jackets. Understanding floating and sinking helps us create safer and more efficient watercraft. Hot air balloons rise because the air inside the balloon is heated, making it less dense than the cooler air outside. This difference in density creates an upward buoyant force, lifting the balloon. The principle behind hot air balloons is the same as that which keeps ships afloat, Archimedes' principle. It's a beautiful demonstration of fluid mechanics in action. The flow of blood through our veins and arteries follows the principles of fluid mechanics. The heart acts as a pump, creating pressure that pushes blood through vessels. The diameter of blood vessels and the viscosity of blood affect how easily it flows. Understanding these principles helps doctors diagnose and treat circulatory problems. Supplying water to homes and cities relies on fluid mechanics. Engineers design pipelines to ensure water flows efficiently, using principles like the equation of continuity and Bernoulli's theorem. The diameter of pipes, pressure, and elevation all play a role in delivering water where it's needed. Proper design prevents leaks and ensures a steady supply. Weather patterns are driven by the movement of air and water, both fluids. Differences in pressure, temperature, and density cause winds, clouds, and storms. Meteorologists use fluid mechanics to predict weather and understand phenomena like hurricanes and tornadoes. The study of fluids is essential for accurate weather forecasting. Fluid mechanics plays a big role in sports. The curve of a soccer ball, the flight of a golf ball, and the speed of a swimmer are all influenced by fluid properties like air resistance and drag. Athletes and coaches use these principles to improve performance and design better equipment. Industries rely on fluid mechanics for processes like oil refining, chemical manufacturing, and food production. Controlling the flow, pressure, and temperature of fluids ensures safety and efficiency. Engineers use concepts like viscosity and Bernoulli's theorem to design pumps, valves, and reactors for optimal performance. Medical devices such as syringes, IV drips, and blood pressure monitors all use fluid mechanics. The flow of fluids must be carefully controlled to ensure patient safety. Understanding properties like viscosity and pressure helps medical professionals use these devices effectively. Surface tension is visible in many natural phenomena. Water striders walk on water thanks to surface tension, and dew forms beads on leaves. This property also helps plants draw water from the soil through capillary action. Observing nature gives us insight into the importance of fluid properties. Capillary action is not just for plants, it's also seen in everyday life. When you dip a paper towel in water, the liquid rises up the towel due to capillary action. This principle is used in ink pens, medical tests, and even in cleaning up spills. It's a simple yet powerful demonstration of fluid mechanics at work. Cooking often involves fluids with different viscosities. Sauces, syrups, and oils all behave differently depending on their viscosity. Chefs use this knowledge to create the perfect texture and consistency in their dishes. Understanding viscosity helps in everything from making salad dressings to baking cakes. Detergents work by reducing the surface tension of water, allowing it to spread and clean surfaces more effectively. This property helps water penetrate fabrics and remove dirt. Understanding surface tension and how detergents work is essential for effective cleaning, both at home and in industry. Ink pens use capillary tubes to draw ink to the tip. The narrow tube allows ink to flow smoothly without leaking, thanks to capillary action. This simple technology relies on fluid mechanics to provide a consistent writing experience. It's another example of how fluid properties are used in everyday tools. Oil spills on water are a major environmental concern. Oil is less dense than water and spreads out, creating a thin film on the surface. Understanding fluid properties helps scientists develop methods to clean up spills and protect wildlife. Surface tension and density play key roles in how oil behaves in water. Aerospace engineers use fluid mechanics to design aircraft and spacecraft. The shape of wings, the flow of air over surfaces, and the behavior of fuel all depend on fluid properties. Mastery of these concepts allows for safer, more efficient, and faster travel through air and space. Construction projects often involve fluids, from pouring concrete to managing water flow on sites. Engineers use fluid mechanics to ensure structures are stable and safe. Proper drainage, water supply, and even air conditioning systems rely on a solid understanding of fluid properties. Nature is full of examples of fluid dynamics. Rivers carve valleys, winds shape landscapes, and ocean currents regulate climate. Studying these natural processes helps us understand the environment and develop solutions for challenges like erosion and climate change. Artists use fluid mechanics in techniques like watercolor painting and marbling. The flow of paint, the mixing of colors, and the formation of patterns all depend on fluid properties like viscosity and surface tension. Understanding these principles allows artists to create stunning visual effects. Advances in fluid mechanics have led to innovations like faster ships, more efficient engines, and better medical devices. Researchers continue to explore new ways to harness the power of fluids for technology and industry. The future holds exciting possibilities as we deepen our understanding of fluid properties. Despite our knowledge, fluid mechanics presents many challenges. Predicting turbulent flow, managing energy losses, and designing systems for extreme conditions require advanced research and technology. Scientists and engineers work together to solve these problems and improve our use of fluids in daily life. Let's recap what we've learned about the mechanical properties of fluids. We explored pressure, Pascal's law, Archimedes' principle, Bernoulli's theorem, viscosity, and more. These concepts are not only fundamental to science, but also have countless applications in our daily lives. Mastering them opens the door to understanding the world around us. As we conclude our journey through the mechanical properties of fluids, remember that these principles are just the beginning. Fluid mechanics continues to evolve, driving innovation and discovery in science, engineering, and beyond. Stay curious and keep exploring the wonders of fluids in the world around you.